So let's start with the linear function, something you're familiar with, y equals mx plus b, where you learned that m is the slope. And what you learned about this slope is that whatever point you choose on the linear function, the slope is always m. So no matter what point you choose, say if you choose a point here, the slope is always the same. If you choose a point here, the slope is always the same. No matter what point you choose, the slope is always the same. And if we put this into our newer notation here, we have the linear function. And in algebra, you probably answered a lot that the slope of this linear function was m. And that's fine. But it's important to remember that this number can also be a function. And in calculus, we say the derivative of the linear function is m, because the derivative gives the slope of the function. And the slope everywhere of the linear function is m. And since m is giving the slope, means that's the derivative. And this derivative is a new function for you. This is a new idea that there's this new class of functions out there, and that these new functions that we call the derivative, these functions output the slope at every point of the original function. Now there's something I want to say about m versus the derivative. So m versus the derivative function is m. Because m, when you were in algebra, you most likely just treat it as a number. It's just some number on the x-axis. But in calculus, we're going to treat this more as a function. Because m, any number, can also be treated as a horizontal line, a constant function. And so in algebra, you most likely answered, well, m's just a number. But for us, the derivative is a function. It's more than just a number. So where we're at right now is that given a function f, there is another function, f prime, the derivative, that outputs all the slopes of the function. And this is what we're talking about, this new function, the derivative. And going back to the last lecture, we did x squared. And this function here, remember this is the name of the function, f. And we found in that last lecture that the derivative was 2x. And we would read this as f prime. So that's the name of this function, f prime. And the prime signifies this is the derivative of f. And again, the derivative always outputs all the slopes of the original function, the function f. So take this scenario. Now here's just a graph. This is the function that I'm graphing. But forget that for a moment and pretend that this is just some hill. And you and your friend are going to stand on this hill. And let's say you're going to stand at point 8. So there's some steepness there that you are standing at on this hill. And let's call that steepness there just M1. Now your friend, we're going to drop down somewhere onto the function here. And we want your friend to land in a position so they have the same steepness as you do. So where on this function, you can see the number line on the bottom here, where on this function should your friend land so that you're both at the same steepness? And let's call your friend, let's say they'll have a slope m2 when they land on the function somewhere. And also recall, remember we read math left to right. So when we read this left to right, something that's going up is increasing. So that means m1 here is going to be positive because it's sloping up. And then over here, this is all sloping down. So we know m2 is going to be a negative number. So for their steepnesses to equal, we're saying that m1 is going to be the negative of m2. That will mean they have the same steepness. m1 and m2 are the same numbers. They're just going to differ by a minus sign. And that's where we're going to drop your friend. So you both have the same steepness. Now to do that, we need the derivative. So here's the function that I'm actually graphing. And check out the practice videos for hand work on getting the derivative. But for now, I'm just going to give you the derivative. And here it is. This is the derivative of the function. And you're standing at 0.8. And remember, the derivative gives us the slope at every point. So if you want your slope, then you just plug your position into the derivative. And so we find then that you're standing at a slope of 0.5625. And we called your slope m1. And remember, our condition is that you and your friend have the same steepness, which means m1 equals minus m2. And so your friend will have to be at a steepness then of minus 0.5625. So here's our picture again. You're standing at 0.8. We just figured out then your slope there is 0.5625, which means your friend would have to have that same number, but the negative, to have the same steepness. And remember again that the slope is the derivative. So we're saying we want the derivative to equal this output. And we can do that. So here's the derivative. And we're going to solve the derivative then when it equals minus 0.5625. We want to solve for the position your friend should be at, so they have the same steepness as you. And so here's an equation. You've solved in algebra. And if you do that, you get x is about 1.5. It's about right here. So if we plop your friend down right there, then you have the same steepness. So I just want to show quick here that if I take just this part here, paste it back in, and if I just take this person and move them up so that connects, and I can draw a line over that connects these, and you can see, at least visually, that they do look like they're at the same steepness. Now, of course, it looks this way, and then we prove it with the math. All right. So this one might be a little bit scary, but here's question 1. Same picture, but now you're going to stand at 0.9. If you stand at 0.9, then where should your friend land so that you have the same steepness? And just to be clear again, here is the derivative that we need, and you are standing at 0.9. Where should your friend stand at? So our condition here is ultimately that we have to compare slopes, which is why we need a derivative to get these slopes. And we'll start with your slope, where you stand at. You're standing at 0.9, so we'll plug that into the derivative, and we get that's about 0.2346. This is the slope that we want your friend to also stand at, but theirs is going to be the negative of that number. And so we're going to take this slope and solve the derivative with this as the output. So we'll set the derivative equal to the slope that we want to have, and then we can solve for the position that the slope occurs at. And we'll find that's about 1.1. So standing at 0.9 means your friend falling down here will have to land way over here at about 1.1. And there you'll have the same steepness. So the derivative is a function. And that's important to remember. The derivative outputs the slope for every point of the function f, or whatever the name of your function is. Maybe your function name is h, or maybe it's m, or it's whatever you want it to be. The derivative is a two-sided limit. Also important to remember. And it's important to remember how this is different from the limits we've been doing. So the limits we've been doing have just been of the output of a function. Now we're doing the limit of this difference divided by h, which is a slope. But the two-sided limit means approaching 0 from the left has to equal approaching 0 from the right. And this is important for an example like this one. And let's look at the input of 3 right here. So we're looking at this point right here, this corner. Now at this corner, the two-sided limit exists at the corner, and this function's continuous at the corner. It's a solid line all the way through. It's continuous at x equals 3. Now remember what the limit of the function is. The limit means as we approach our point of interest, which is 3, we ask, what output are we approaching? So if we approach from the left, we're approaching an output of 8. And if we approach from the right, we're also approaching an output of 8. The left and right equal, which is why we say the two-sided limit exists. But the derivative is different, because the derivative, the left side limit of the derivative, does not equal the right side at 3. Because remember, the derivative deals with the slope of the function. So as we approach 3 from the left, the slope is approaching this steepness. As we approach 3 from the right, the slope is constant. Constant is a slope 0. This up here is certainly greater than 0 since it's sloping up. These don't equal. The left derivative doesn't equal the right derivative. And so we say the derivative doesn't exist at this corner. We say the function here is not differentiable. We can't differentiate it. So try this for question 2. Where is this function not differentiable? So what you want to look for are sharp corners. Because at a sharp corner, if we approach 0, so the answer here is 0, where is the function not differentiable? Not differentiable at 0. Because if we approach 0 from the left, the function is approaching something that's sloping down very steeply. But if we approach from the right, the derivative is actually doing something that's sloping up very steeply. So again, if you look at this slope, you can see the slope from the left is going down. But from the right, the slope is now going up. And there's no smooth transition from down to up. It's just immediate. It's a sharp corner. And the derivative fails then at 0 because the left and the right side don't equal. So here's a tough one, because I haven't mentioned this yet. Where do you think this function is not differentiable? Now the answer here is also 0. The function is not differentiable at 0. And now this is for a different reason and why the derivative fails here. And this is the requirement that the derivative is a function. And remember, a function can't be a vertical line. If you recall the vertical line test, or that one input can only have one output. That's a function. And right at 0, the tangent line here is a vertical line. The slope of the derivative would be a vertical line here. But the vertical line is not a function. And so the derivative fails at vertical lines, vertical slopes. So a little bit or two more things of terminology I have to say here. And let's just go back to the standard setup for slope on a curved function. And so if we take our 2 points and just connect them with a straight line, in general, we call this the secant line. So if you take any 2 points on a function and connect them with a straight line, that's a secant line. And a secant line is also called the average rate of change. So we can get, let's call this point A and point B. We can get to point A from point B by following the function. Or we can find the average and just follow the average to get to our destination. And so that's why this is sometimes called the average rate of change, the secant line. And a secant line is a linear function. And m for the secant line is the standard slope formula. So you would just take your inputs. Remember, your inputs would have to be given to you. So you'd have to be given x1 and x2. And you'd also have to be given the function. And so you can figure out all the information here. And the y-intercept if you need to, which I will work through in some of the practice problems. Now, another line we have has to do with where we're at our point right here, our actual point of interest. So imagine you're just standing here, and there's some steepness, some slope you're standing at. And this line here that represents the steepness you're at, your slope you're at, right at this point, we call the tangent line. The tangent line is also called the instantaneous rate of change. In other words, how are things changing right now, right at this very moment right here? And again, this blue line is just a linear function. However, the slope of this blue line is the limit of the slope formula. And remember that this limit is ultimately the definition. And remember, this limit is ultimately the definition of the derivative. In other words, the derivative gives you the slope of the tangent line. So just putting them together, the average rate of change, take 2 points, connect them with a straight line. That's the average rate of change. However, the instantaneous rate of change, the change that's happening right at this moment, is given by the derivative. So in summary, the derivative is a new function that you're learning. And this new function outputs the slopes for the function f. The derivative is a function. And what this means then is the derivative cannot output vertical tangents, because a vertical line is not a function. The derivative is a two-sided limit. And what this ultimately comes down to is that in order to take a derivative, the function must be continuous with no sharp corners. If the function is continuous with no sharp corners, then it is differentiable. The derivative is not differentiable at holes, gaps, sharp corners, and then finally, there was then the secant line, which gives you the average rate of change, and the tangent line, which is the instantaneous rate of change. And the derivative ultimately connects with the tangent line. I'll talk to you in the next lecture.